One way to think about scientific questions is in terms of comparing different hypotheses or trying to understand the evidence that supports a given hypothesis. But what is a hypothesis?
A really good hypothesis is a statement about an idea, right, that can be proven right or wrong. And proven right is very difficult. You can just accumulate evidence that continues to be in support of that idea. The stronger statement is when you can prove a hypothesis false. In that sense, the hallmark of a good hypothesis is that it is falsifiable.
More or less every scientific question can be boiled down to comparing hypotheses. You can hypothesize that a phenomenon does occur, doesn't occur. You can hypothesize that a phenomenon occurs rarely versus commonly. Not everybody thinks of scientific questions as being a set of testable hypotheses like I do. But I think in essence, when people ask scientific questions, they are really trying to get at comparing this idea of how things occur, why they occur, when they occur, and all of those come down to asking and making a simple comparison of different underlying models. Now, of course, this is in biology. The underlying models are often unknown. We really cannot always model what's going on in biology. But nonetheless, I think as we start to understand the way biology works, as we understand more and more mechanisms of the essence of how biology operates, we realize that in the end, we are actually testing hypotheses whenever we're asking scientific questions within biology.
And I think that there's a healthy mix of hypothesis-driven and non-hypothesis-driven work to be done in the world. Not every experiment that you ever do will have a really strong hypothesis motivating it. In particular, a lot of work in the sort of what is there space is not hypothesis-driven, right? But how does it work should be hypothesis-driven. I've learned a lot about how to create good hypotheses because I tend to like more philosophical questions that live in the what is there or why is it like that space. But if we're in that middle space of how does it work, it's really important to sort of commit to a specific idea such that you can use it to frame the experiments that you're going to do.
The essence of asking a scientific question, to me, is to try and refine a set of hypotheses that you're testing down to ones that are manageable, that are understandable, that are interpretable, and that are, of course, testable. The way that you refine a hypothesis is as varied as the different types of scientific questions that one can ask. There isn't a single method for trying to come up with testable hypotheses. It's very extremely context dependent. But that doesn't necessarily mean that there aren't some general characteristics of what good testable hypotheses are.
An example of a specific, testable, falsifiable hypothesis is local interactions between transcription factor 1 and transcription factor 2 cause transcription factor 2 to behave as an activator. That's a very specific statement, right? And we actually spent weeks figuring out what that sentence would be, right? And there were parts of it that were important, right? Local interactions, right? So notice that we didn't say interactions between because that's too vague, right? So local interactions is what we meant. So they have to be bound near one another on the DNA. And we could have used even more language to make that sentence even fussier about what we meant. And local interactions between TF1 and TF2, right? Not all transcription factors, these two, cause TF2 to behave as an activator. And so that means, very specifically, if we mess with the local interactions, we should get TF1 no longer influencing the behavior of TF2, right, to behave as an activator. And so I think that that example shows a couple of important things. The first one is that a hypothesis can be vaguely stated, something like transcription factor interactions can influence the activity of the transcription factors, right? Like that's a very broad hypothesis, and it may or may not be true for every set of transcription factors and all of their behaviors, right? Thus, it's very hard to falsify. And the other thing is that the wording matters, right? And so it can be really helpful to write hypotheses in the context of your specific project because it forces you to be deliberate about your language and what parts of this hypothesis you can test and which parts you cannot, and how generalizable your conclusions will be. It forces you to be really honest about whether or not you're trying to leverage a single example into a general case, or if you're trying to analyze a very general case, say genome-wide, right? Then you might need to articulate your hypothesis in terms of averages or correlations or something like that, as opposed to specific mechanistic interactions, right? So it's a cycle, right? You write down a hypothesis, you think about the experiments that you could do to test it, and then you think about whether or not those experiments really actually get to that hypothesis and try re-articulating your hypothesis until those things actually close a loop, like close an intellectual loop, to help you understand the limits of your ability to interpret your data. One of the big pieces of resistance around crafting a hypothesis is if you feel like being sort of for or against it is sort of equally probable, right? You don't want to like draw your line in the sand as this being your hypothesis because you think it's you feel pretty ambivalent about whether or not it's true. And there, it's really important to remember that it doesn't matter. It's a straw man, right? Like you're going to put something down such that you can test it, and realize that there are alternative or sort of reverse versions of your hypothesis that are equally valid and may become more valid after you do your experiments.